time that I am in Brazil, and I'm very pleased to be here. Thank you to Claudia and Hasna for the opportunity to come and participate in this event. So when I look at the program, well, let me also first mention that this is a joint work with my collaborators, Jose Luis Perez and Kazu Yamasaki, and Kazu is here in the audience. Okay. Okay, so when I look at the program, I realize that I mean, the common word is optimization, but certainly there are different approaches to optimization, and my field of expertise is optimal control. And then, well, I thought that it would be a good idea to give a good introduction to the problem that we wanted to look at for all the audience. Okay, so. Okay, so this time I'll talk about this optimality of refraction strategies for Lévy process. And let me tell you about the very short story about the problem, okay? So suppose that we have a Brownian motion that we want to control using absolutely continuous strategies, okay? And the point is, what is the optimal one? Of course, we need to pay a price for that, okay? We need to pay some cost, and the problem is to find the optimal strategy to do that. That's somehow a short story of the problem, okay? But we would like to do that in a simpler way, let's say it, okay? And we would like to find a simple structure for the optimal strategy for the controller, okay? Okay. Okay, so this is the outline of the talk. So I will start with some motivation for the problem, formulate the control problem, and give you some idea of the methodology that we plan to use to solve this problem. We will rely on the methodology of scale functions. That's what we plan to use to prove a simple structure for the solution of the problem, okay, that I mentioned before. We apply it to Lévy processes, spectrally negative, and I will also show some connections with singular control problems and show you some numerical results at the end of the talk. Okay. Okay. So let's start with the very simple motivation, as I said. So consider a Brownian motion. Okay, everything will be in one dimension here. Okay. So we have a one-dimension Brownian motion, and we have some controls that we plan to use, L sub t, and they will take values in this interval, 0 delta, okay? And the problem is the following, okay? So we have some dynamics for the controlled process U, which will be described in this way. U sub t is the Brownian motion plus some effort that we plan to put in order to move it, okay, in an optimal way. And we have some initial conditions, and k is somehow the drift function that will move the Brownian motion. Okay, of course, the controller has some objective in mind. Okay, and let's suppose that the controller has this objective. So we have this cost function h, this count parameter q. Okay, and well, for each control that we choose L, then we have this value function, and well, something that is very well known is that this problem, if we want to minimize this function among all the controllers, then this is related with this HGB equation, okay? Then the end of this story tells that if we can solve this HGB equation, we can derive somehow an optimal control, right? This is dynamic programming, classical dynamic programming. So this is verification, okay? So if we can find a smooth solution to the HGB equation, to this HGB equation, then we can just propose some candidate for an optimal control, and it will be the arc mean of this quantity here. Okay, this is very well-known facts for dynamic programming, okay? And then, of course, the question is, in general, is how can we find this optimal control, okay? And if there is an easy way to calculate that optimal control, okay? Of course, there are numerical approaches, okay? as they were mentioned. But the problem that we want to look at is this one. Okay? Under which conditions on the data of this optimization problem is it possible to obtain a simple solution? Okay? By the data, I mean the cost function, the running cost, the delta, which appears in the control set. Okay? And this is related with another. Let me explain what I mean by simple here. Okay? And let me recall a couple of problems where we have what I could say is a simple solution. And it is the case of a singular control problem or an optimal stopping problem. Okay? I mean, in the singular one, we have somehow some partition. Let me draw my pictures in R2, but everything will be in R here. Okay? So for the singular control problem, this morning, Daria mentioned the problem of Neumann conditions, with Neumann conditions, where basically the strategy for a singular control problem says, well, we have two different regions, okay? When we are inside, we do nothing. We just leave the process live as it goes. And then when we reach the boundary, we need to reflect it somehow, right? This is for a singular control problem. This is somehow simple because you do nothing most of the time, and when you reach the boundary, you just project it inside, okay? The other case is for the optimal stopping problem. And in this case, you just leave the process live as long as it reaches some boundary, okay? Again, we have two different regions, okay? And when it reaches the boundary, we stop the process, okay? This is somehow the kind of solution that these two problems have, okay? So we have a division of the state space, and in one part of the region we don't do anything, and in other part of the region we control the process or we stop it, okay? Okay, so this is the problem, and that's what we understand as a simple solution for the problem, okay? So this is what I was saying about the singular control problem, okay? So suppose, I mean, in the previous framework, we had this structure on the dynamics, so we have this integral part of k of L sub s, okay? Now, for singular control, we may change it, okay? So we have all the effort of the controller summarized in this integral part, okay? And then for this problem, we have exactly this form of solution in general, okay? So we have free boundary problem, and we want to reflect the process in that boundary, okay? This is the form of this remark here somehow summarize what the HGB equation, the corresponding HGB equation says, okay? And the question is if it is possible to have something analogous for the absolutely continuous problem, okay? And by analogous, of course, I'm not saying that we will have some reflection of the process. But what I do mean is that we may have some refraction of the process. So in other words, what we are looking is for solutions, for optimal solutions of the original problem where we may only change the drift of the Brownian motion. That's somehow the questions and the kind of solutions that we would like to have. Okay? So that's a very basic problem, very simple to propose, and I'll tell you the story of the solution, okay? Okay, now the rest will be somehow a bit technical to tell you what is going on, but okay, so this slide is just to say what this Laplace exponent of this Lévy process somehow summarize all the information that I need of the process, okay? So here I have the second order term, the drift, and the jump measure that Daria mentioned this morning, okay? For the Lévy process, okay? So I'm talking about a spectrally negative Lévy process. It means that we have jumps only downside jumps, okay, of the process. And here, well, of course, I need to do some technical assumptions on the Lévy measure. So I'm assuming that the support of the measure is in this set with this integrability condition, okay? And, well, as I say, most of the information is here, and here are some remark on the process, okay? So there are some cases where the process may have some paths of bounded variation. It is in the case when sigma, the second order term, disappears, okay, together with this integrability condition. And in this case, then the Laplace exponent will have this form, and the number that is here is just a change of the original gamma that we had before, okay? And then we have to exclude this case, okay? Well, this will be the filtration generated by the Lévy process. Okay, so this is the information of the process that we want to control. And the control problem we want to look at is the following. So we have some beta, some real number. This delta is also a fixed number. Remember that 0 delta is the control set, okay? Let me put it here. That's where all the controls take place, okay? Okay, so I will look at the absolutely continuous strategies, okay? So it means that they will have this integral form. So I'm taking k equal to the identity, the example that I presented in the motivation, okay? And, well, these processes elsewhere will take values in this compact interval, and this will be the cost function that I am interested in, okay? So this is the running cost h, depending only on the state of the process u that I defined before. I haven't defined u, right? I did it? No. Oh, yes, here is u. Okay, so u is the original Lévy processes. I am subtracting the integral part of the absolutely continuous process. Okay, that's what is capital L. Okay, this is capital L. And the second part, beta times the control L sub t, okay, which represents basically the energy that I have used up to time.
Just for clarity, is L phi t random?
L sub t?
Yes, to the previous slide. Can you go to the previous slide? Sorry, the next slide where you have ut. So L phi t is adapted to.
Yes, sure. Exactly. Yeah, it is adapted to the filtration that I mentioned before, this one. Yes. Okay. So this is the value function, okay? Well, this is the cost function associated to this strategy, L sub t, okay? This is what we call the net present value. The state process then is the Lévy process x sub t modified by the integral part of the control that I am using, okay? to modify the trajectory of x. Okay, and the objective then is to compute the value function b of x, which is the infimum of the b sub pi. And well, another objective is to find an optimal strategy where this infimum is attained, okay? And an extra objective of this problem, of course, then is to find a very simple form for the strategy. Okay, for the optimal one. Okay, here are some technical hypotheses, okay, on the model. So when x is of bounded variation, then we make this assumption. We need also this integrability assumption, and the function h, this turns to be very important. H is a convex function, and it has some polynomial growth in detail, okay? So these are the technical assumptions on the data of the problem. okay, let me make a small remark, but which is important, because suppose, I mean, recall that delta is the upper limit of this control set, okay? So suppose that we use as a control, the most energy that we can, okay? So this is a particular strategy, right? So we can define y. So in this case, we are just changing the drift of the original Lévy processes, subtracting delta, okay? So as it is said here, so we are just using the maximal value of the control, okay, to modify the process. Another important remark, so this is also a Lévy process, okay, and this is again a spectrally negative Lévy process. That will be important in the future. And the other important thing is that the cost function b sub pi is well defined and finite, okay? So this comes from the hypothesis that we are putting on the model. And an important remark is that we can also consider a version of this problem. I mean, you may ask why we wish to subtract here the control, right? So why we don't put a plus instead of a minus, okay? So this is a small remark that will be useful also. So we can consider, in fact, the case where we can add the increments, okay, the drift, the control, okay? And in this case, the problem will change to this one. Instead of the other one, we will have this one, okay? But the important point is that when we have here a plus instead of minus, okay, then the problem is equivalent to the problem that I described at the beginning, okay? And the reason is that we can use y. Y is the process that I mentioned before when we use the total amount of energy, okay? And set this L sub t pi in this form. We can write L tilde in this form, and then we write the value function b sub pi in this way, okay? So what we have is that both problems are equivalent using different beta. That's what happens, okay? Now, let me give you also some idea of the problems that we had in mind to study these problems and the places where this could be potential. This could have potential applications. So we may think that xt may represent the inventory level of some company, okay? And then the objective of the company could be to maintain the inventory level around some target x hat, okay? So this function h somehow is penalizing that the process goes too far from the objective, okay? That's what it is doing. So this function h can be used to penalize the distance between the process xt and the objective x hat, okay? And well, you can think in different products where you have your stock. I mean, it can be oil, coal, water, whatever. Okay. Okay, now let me be more precise about what I mean by refraction strategies, okay? So we will say that P sub b, okay, is the type of control process that I presented before, and what is happening is that I mark some point B in R, okay, and what is happening is that before B, this process is just like X, okay, and when I am above this specific level B, then I'll change the drift of the process X, okay? So I'll change it by delta. Remember that delta is this number that appears here, okay, in the control set, okay. So this is what I mean by a refracted process, okay. At some point, I'll change just the drift, okay, and well, it turns out that this is a Markov process, okay, and it is a unique solution of this stochastic differential equation, okay. Okay, so this summarizes somehow what I said before, okay, about the behavior of the process X, okay. And then let's look at the cost of using this kind of strategies, okay. Okay, then it has this specific form. So the cost associated to this strategy can be written in this form using this indicator function here when we are above the level B, okay. So B somehow is parameterizing this set of strategies, okay. That's what I am doing. So the original problem was an infinite dimensional, of course. This is a finite dimensional problem. Okay. Okay, now the idea is, is to use the scale functions to write this expression, okay? So I will first put my attention in this type of strategies, the refraction strategies, okay? And I will show you how to write this function in terms of scale functions, okay? Okay, so, and this is what I have here. So the net present value, the cost function associated to this refracted strategy, okay, can be expressed in terms of scale functions of two Lévy processes, X and Y. Y is the process that I introduced at the beginning, okay? And then, what are these functions, these scale functions? Well, these are basically Laplace transforms, okay? Which, I mean, let me just mention that these scale functions have been quite useful to study the excursion of Lévy process. And they have been a very powerful tool to have closed form expressions for to understand the behavior of this Lévy process. At the end, I'll give you some references for that. But, well, let me put it in a simple words and then mention that these are mappings. Okay, these scale functions will be a map from R to 0 infinity. Okay, and they have these properties. Okay, unfortunately, I use the yellow one. And I cannot read it from this side, but anyway. Okay, so they satisfy this equality here. Okay, the first one, we have two different Lévy processes, X and Y, and we have one for each one. Okay, so the function that is here and here are defined in this way. Okay, and we have this property of this function, C and capital C. Okay. And, well, I need to be a little bit technical, but I'll give you some, I need to give some ideas on how, what are the tools that are involved in the expression, okay? So we need the resultant measure of the process, which is defined in this way, okay? So this is the controlled process. What we have here is the exponential distribution with this parameter Q, okay? So this is just the distribution of the process, the controlled process just to B, okay, and it has this expression. And the point is that this resultant measure, it has some density which can be written in this form, okay, as a sum of these two functions, R super 1 and R super 2, okay, and the expressions for these densities which are here are given in terms of the scale function that I mentioned before. And it is an awful expression that I didn't want to put here because it may not say anything. But what is important to mention is that the cost function, when we use this the strategy which is refracted at level B, okay, can be decomposed in this as a sum of these two terms, these two functions. One is related with the position of the variable x, okay, this second one. Okay. Now, once I have a parameterization of the cost function in terms of a parameter b, okay, what I want to look is at the minimum, okay, between all those strategies, okay. But at this point, this is a problem which depends only on the parameter b, okay. This is a function, a real valued function. So I can use basically calculus, okay, to find or to propose an optimal solution, okay. So these are the first order conditions that we may need, okay. So we want to minimize over all the possible places where I can use to change the drift of the process, okay. So I'm using just those conditions, okay, which are here. So what I would expect is to find some b star such that the partial derivative of this function is equal to 0, okay? And this is my hope. And what is interesting is that when I take the derivative of this cost function with respect to b, it has this nice expression, okay? In terms of this is the expectation of this in terms of the h function and the derivative of the cost function b. Okay? So then the idea is to look at this b star, to find this b star where these first order conditions are satisfied. Okay? This is the complete idea. Okay? And of course, if we take this equality and put it here, then I'll get this identity in terms of the derivative of b with respect to x and this expectation, okay, in terms of the first derivative of h. Okay. Well, this is some proposition that I put here. I mean, it is an awful expression, but what I want to transmit to you is that the derivative that I mean use, the derivative of b, okay, can be written as a product of two things, okay? This expression, which is in terms of scale functions, and this other expression, which depends on b, okay? And then, if we go back a little bit, what we want is that this u is equal to 0, right? In other words, we want that this product here is equal to 0, okay? But it turns out that the first one is strictly positive, so somehow this I of b has to be equal to 0. That's the one that could give us the solution, okay, to the first order conditions. Now, let me give you a couple of examples, okay? Very simple examples. So the case where h is a quadratic function, okay, alpha times y squared, okay, and in this case, the b star where these first order conditions are satisfied, it has an explicit form, okay? It has this form. This is everything is in terms of the parameters of the data of the process, okay? Alpha, q, and the discount factor, the beta, which appears in the cost function, and this is the minimum of the Lévy process until this time, until this exponential time, okay? This is the one that I introduced before. Well, just to say it, I mean, this function I, for this example, it has this expression, okay? This awful expression, okay? So I will not explain much. I will not spend more time explaining all these terms, but it is quite technical. But let me jump to another simple example. This is the case when H is linear, okay? So in this case, the B star is equal to minus infinity when we have this relation between the parameters, okay? So what it means that B star, what would mean that B star is equal to minus infinity? It would mean that we will never change the drift, right? And while the other case, B star equal to infinity, what it says is that we change the drift to the maximum one, right? Okay, so this for the Lévy process, this will be the infinitesimal generator, okay? Gamma applied to smooth functions, and we have this verification lemma, okay? So this is, I mean, we would like to find a refraction strategy as an optimal strategy, okay? That's the objective, to prove that it has that form, okay? So very easy. You use all the energy, okay, when the process is above some level, B star, okay? And otherwise, you don't do anything, okay? Okay, so this is a verification lemma. So suppose that we have some strategy. This is not necessarily a refraction strategy. It's any strategy, okay? And suppose that the cost function is sufficiently smooth, okay? Then, and satisfy these two inequalities, okay? This is the operator that is here, the cost function. If we have this restriction on the gradient, on the derivative of B, okay, and otherwise we have the solution to this inequality if we are above the level beta, okay? Then it is possible to prove that P hat is an optimal strategy, okay? This is the first result. And then, okay, the idea is then to apply the previous result, okay? And to apply it to the solution that we got for the B star, okay? That's the idea, okay? So the idea then is to show that the function associated with this refracted strategy is sufficiently smooth and satisfy the hypothesis of the verification lemma, these two inequalities, right? That's the idea, okay? So I have a candidate for B star. That's the one that solves the first order conditions. Then I have a verification result. So I will apply it to this lemma, okay? Okay, so this function is sufficiently smooth, okay? And one can prove also that the two inequalities that we have here, when we use refracted strategies, it has this form, okay? So in other words, the inequalities that appear in the hypothesis of the verification theorem will hold if the derivative of x is bigger or equal beta when we are above the level B star, and otherwise we have the other inequality, okay? And these are other properties of this cost function, okay? It is convex, and one of the conclusions is also that this cost function satisfies this hypothesis, okay? So in other words, this is to say that the strategy, the refracted strategy, used at this level B star is optimal, okay? And the value function is given in this form, okay? This is somehow the conclusion of the talk. Now, together with this, we also wanted to study the limit when delta goes to infinity, okay? So this delta, which appears in the control set, okay? So as you may imagine, the limit will be some kind of singular control problem, right? And, well, let me recall something. So this is the value function that I introduced, okay? Doing some change. When I work with the with the Lévy process, that I change the drift using the delta limit, okay? But with plus here instead of minus, okay? So this is the relation between these two value functions. This is the original one. This is the modified one somehow. Okay, so this is the relation. Okay, so we want to pass to the limit when delta goes to infinity. That's the objective. Okay, and then let me call this set by sub infinity the set of admissible strategies. So they are right continuous, non-decreasing adapted process, okay, starting at 0, okay, and then we can define this value function. That's the infimum of this expectation, okay? So in other words, I am considering the case when delta is equal to infinity, okay? And well, it can be proved that the infimum for this problem is attained, the limit is attained at a reflected Lévy process, okay? And the reflected, the optimal strategy, it has this form. So it will be reflected at this level, B star infinity, okay? That's what it is saying. Okay, so what's the conclusion? This number is defined in terms of the unique root of this function, okay? And to summarize, I mean, this is the B star delta is the one that we use to control the problem, okay? When we had as a control set this one, okay? This is the one that we found solving the first order conditions, let's say, okay? So what we prove is that this number converges to this one, okay? And that this value function, okay, converges to this one as delta goes to infinity. That's what we prove. So somehow, that's how the way the intuition works, right? That we may, in the limit, obtain a singular control problem. Okay, here are some numerical results. Here, for these examples, h is the quadratic function, q is equal to this number, and we have this kind of approximation using Weibull random variables, okay? And what we have here is the graphics of some value functions, okay? This is the net present value, this is x, okay. And this is some plots when delta goes to infinity, okay? So these are the limits. Okay, so here are some references. I mean, the results that I presented are based on this paper. But there are some previous work. I mean, most of the what I say about or we use on scale functions. I mean, there are a lot of work done by Andreas Cipriano, Lefebvre, Palmowski. Okay, here are some names, And there are also some related work done by Eric Bardot and Casu, which just appeared last year. Okay, and well, this other work is related with games when we have singular control and stopping at the same time. Okay, well, thank you very much for your attention.
Thank you, Daniel.